Good afternoon.
Hello.
Hello there.
All right, folks, we're going to get started here. And what we're going to be talking about today will be the acetoacetic ester and malonic ester syntheses. The acetoacetic ester synthesis starts with this compound here, which is called acetoacetic ester, or AAE. And this is malonic ester, which is the ester of malonic acid. You might have heard of malonic acid, especially if you're familiar with the carbon, the carbon cycle, not the carbon cycle, the Krebs cycle. Yes, the Krebs cycle. All right. Or citric acid cycle, that's the other name for it. Okay. So what the acetoacetic ester synthesis does, or the malonic ester synthesis does, is it allows us to make, for the acetoacetic ester, any methyl ketone you want. And for malonic ester, if it's a starting point, it allows you to make any carboxylic acid that you want. Now, all of this is predicated initially on one observation. For compounds of this kind, the hydrogens here are actually quite acidic. So the pKa of these hydrogens is around 11. Now, what does that mean? Well, consider some other pKa values. If you've got just one carbonyl group, the pKa is about 23. Now remember that this difference doesn't mean that that's twice as acidic. That's 10 to the power of 12 times more acidic if the pKa is that much lower. So it just gives you an idea. The pKa of water, or we'll say it water here, is about 14. So it gives you an idea. It's more acidic than water is. Now the reason for that is because when you lose one of these hydrogens, you end up with an anion, and that anion is stabilized by not one, but two carbonyl groups. So there's lots of different possibilities for resonance of this negative charge between two oxygens here, thus making this hydrogen much more acidic. So lots of resonance opportunities are existing here. I'll see if I'll draw a couple of those. Sorry, I shouldn't have put that where I put it, but anyways, it gives you an idea. And then the negative charge here can come back down, and then it can go up onto the other oxygen. So there's lots of different ways this negative charge can be moved around to have it stabilized, which is why this hydrogen here is going to be fairly acidic. Does anybody have any questions so far? All right, so the bottom line here is that if we treat this with a base, and the base we're using here is sodium methoxide. I like to call it Naomi, see, because it's Naomi, and it's in methanol, MEO. So it's a strong base. It's the conjugate base of methanol that we're using here. So that's going to, so I'm just doing the first step here, and you can see that that's going to give us the negative charge in the middle here. And you'll notice that it's this hydrogen off here that gets removed, and not this one. You might think, well, that one's fairly acidic, but it isn't. The pKa, the one in the middle, is much lower, so it's much more acidic. So it's this one that gets removed, this hydrogen here. In the next step, we can add any alkyl halide. It could be an iodide, it could be a bromide, or anything you want here. And that'll be the first step. What it will do is it will, well, I'll just shortcut this a little bit. It will allow you to put that entire alkyl group here off the middle, like that. And then we can repeat the same process. So I split that up into two steps. I'm just going to do this as one step now. And we can put another group of your choice on. And I'm just going to choose something else here. And I'll make it a bromide this time. And it will do the same thing. There's one more hydrogen here that's acidic that can be removed, this one. And that allows us to get this grouping attached like that. Okay. Right, tell me how you're feeling about the first two steps of this process here. How do you feel about this process so far? 5, 4, 3, 2, 1, 0. 2 people aren't voting. All right, any questions? Any questions? Well, 5 of you halfway understand it, so I'm just trying to determine what's going on here. The whole point of what I've just done so far is just to get 2 different alkyl groups attached at that middle point there. All right. Well, if you're not going to tell me what's up, then I can't help you. The next step is hydrolysis. And what will happen here is the ester will get hydrolyzed to a carboxylic acid. This is a reaction that we dealt with a lot back in test 3. And then what can happen is we can heat this and we can lose the carboxylic acid group. So I'm going to, well, I'll show the final product here. Plus CO2. Now the mechanism goes like this. The first step here is rotation of a carboxylic acid group and then we get this electrocyclic process occurring, which causes the decarboxylation, which leads to the carboxyl group coming off as a CO2 and giving us this methyl ketone here. So you can see that depending upon what we add, we can add whatever we like to end up getting any kind of methyl ketone that we want. Does anybody have any questions so far?
Yes, so can you explain where is the third arrow going? So one is going from the double bond oxygen attacking the hydrogen, and then that bond.
Okay. I did kind of skip a step here. I will let me put the other step in. I didn't put in the enol step, Miriam.
Oh.
You always keep me on my toes. You always keep me on my toes. All right, let me do that. Oops. And then that turns into a ketone by the enol steps that we learned about the other day. So that's that kind of that intermediate step I didn't show. But do you see where all the arrows are going now?
Yes, thank you.
And how the CO2 kind of breaks off there when that bond breaks. All right, anybody got any other questions about this? The mechanism here actually isn't really too relevant to the kind of problem you're going to see on the test. This is actually going to form the basis for the synthesis problem that you're going to see. And I'll show you how that works in a minute, and you'll find that it's not really that bad. So the other possible kind of thing that we can do that's related to this is the Malonic ester synthesis. And you can see that we're still dealing with the same kind of system, except that instead of a methyl group on the left end, we've got essentially an ester group, a methyl ketone group on the left hand. We've got an ester grouping on the left hand. And the other difference that we're going to see here when we do this is that once we get these two R groups attached, or the R and the R primed, we add H3O plus, and that will actually hydrolyze both sides and cause it to become a dicarboxylic acid. And then by a similar mechanism, one of these can break off, but only one of them to be left with a carboxylic acid. And it doesn't matter which one of these breaks off because it's symmetric anyway. And we end up getting a carboxylic acid as a product. So that both of these methods allow for us to make one or other of something we might need. And it's all very versatile because we can use whatever alkyl groups we need to in order to attain our goal of getting either a methyl ketone or a carboxylic acid, depending on what we want to start with. Does anybody have any questions so far? All right, so let's look at an example. So let's say that you wanted to prepare this specific methyl ketone. So what you'd have to do is this is the end product which you're given here, okay? The end product. So what you would do is you circle the groups attached to the carbon connected to the acetyl bond O. If you remember, I call this the alpha carbon. So we look at the groups attached to that, and those will form the basis for deciding on what R and R primed are in the process of making each of these kinds of compounds. So this one for the methyl ketone, this one for the carboxylic acid. Now, methyl ketones will always be made from this compound, acetoacetic ester, which has the methyl group on the left. And carboxylic acids will always be formed from malonic ester, which has an ester grouping on the left here instead of a methyl grouping. But the method, again, is going to be pretty much the same. So the groups attached are going to be a methyl and an ethyl. So we need to use methyl iodide and ethyl iodide as our R and R prime groups. The order in which they're added does not matter. I could have put the ethyl group on first and then put the methyl group. The other thing is that it doesn't have to be an iodide. It could be a bromide, a chloride, or an iodide, and it doesn't really matter which. And then you go ahead and you just show the addition of each of those, and then you come up with the product at the end, which is the one that we wanted. So again, starting out with acetoacetic ester, the methyl group on the left, we end up getting a methyl ketone as a product. Starting out with the malonic ester, which has the ester grouping on the left, we end up getting a carboxylic acid as a product. Does anybody have any questions so far?
Yeah, I do.
Yes, Julie.
So I understand what you're saying, but what I don't understand is, I guess, the way that it's written. So when you put the NaOMe and the MEOH on the top,
Mm-hmm.
okay,
That's the base, yeah.
and that's always going to be that for
Yes.
either one, right?
Yes, yes, yes.
And then you put the methyl and the ethyl group on the bottom. But on the other one, when you were showing, you had a hydrogen as number 2 step.
Hydrogen is number 2. I don't think
You had
so.
I thought you had an H.
Oh,
H
no. Now, what I did was I split it up into, the first time I did it, I split this into 2 steps to show what the base did and then what the other thing did. No, I never.
So that's going to always go there in the first step, and then the second step will have the methyl and the ethyl groups that are in there.
That's right. Or whatever groups you want to add. These are the things that are going to vary, Julie. Whatever's in 2 here on each of these, that's what's going to vary. And obviously then the groups attached to the central carbon are going to vary in accordance with what you put for each of these.
Okay, thank you.
And that's it. Everything else is going to pretty much remain the same from problem to problem.
So you're never going to see the H plus in there as part of it.
Well, the H plus, if I was talking about it, would be added here when we hydrolyze the ester.
Right. Okay.
I think that might be what you're thinking of.
Yeah. Thank you.
All right. Let me show you how this looks on a test question. Yeah, and I said I was going to add some more tests, and I will. At least one more. Hopefully 2. We'll see how it goes. All right, let me get rid of that too. All right. Where are we? Here we go. All right. So here's an example. So I'll redraw this. So the first thing you'll notice is that it's a methyl ketone. Right, that's a methyl ketone. So the starting material for this one is going to be this compound here, acetoacetic ester, which has the methyl group on the left end, and not the other one, which was malonic ester. Had this been a carboxylic acid, in other words, had this been an OH here, where my cursor is, where I'm circling, then you would use the other reagent, malonic ester. All right, so that's going to be your starting point. Now what you'll do, take a look at the groups attached to the alpha carbon. But be sure also to make sure that you I'll show you in a second. So it's going to be Naomi. And Mio. And then we put in our group here. Our group is going to look like this. And then I can put an I or a BR or a CL on that. And then that gets added to the first one at the middle carbon. You got to be careful of how you count the carbons here, but that bond there is new. Does anybody have any questions about this so far? All right, let's see how you feel about it. How do you feel about this so far? How do you feel about this so far? 5, 4, 3, 2, 1, 0. 2 people not voting. Okay, any questions? Any questions so far? Yeah, if you don't tell me, I don't know. So it's some of you say you halfway understand this, so I don't know what's going on. Okay. So the other grouping is going to be this one. So again, the base is going to be the same thing. And the grouping that we're talking about, and I'll put a bromine on this time, is going to be this one. So hopefully you can see what I did there. I just took that entire group, and where it joins onto the middle carbon, that's where I put the bromine. But remember, it could be a bromine, an iodide, or a chloride. It doesn't matter which, really. And the compound I end up with at this point is going to be this one. So that's the first grouping, and the other grouping that we just added will be this one. Does anybody have any questions? Now the second to last step is the hydrolysis of the ester to give the carboxylic acid, and we've got this grouping down here, and then we heat this, which will give this final product here along with CO2. I just don't want to redraw it, that's all. And we'll get CO2 as a product there as well. But there's your, that's how you would create that compound there. Does anybody have any questions?
I do. When you added the second reagent, can you count the carbons for me?
Sure. So we got, I'll write them in, okay? So we've got C, 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 and C, and of course there, right? And then when we put it on here, we got the 3 C's, and then the C here and a C here, and then all the C's in that ring. And then here they all are, here and here and here and here and here.
Where does the other H go?
Which other H are we talking about?
Well, when you take off that whole section, you're taking off an OH and you're taking off a C double bond O, and you've got the CO2. So where does the other H go?
This H ends up right here. Right, do you see where I'm pointing the cursor?
Yeah.
That's where it ends up.
So it moves over.
Yeah.
Okay.
So and the process by which it moves over, you can go back and take a look at that mechanism I showed you earlier, Julie. And you can see how that hydrogen ends up on that carbon after all the arrows move around. All right, any other questions? So on the test, you can expect either this starting compound here to be a methyl ketone like this one, or it could be a carboxylic acid. If it's a carboxylic acid, the only difference is that you'll start with malonic ester, instead, but you'll use a similar process in order to get the answer. All right, how do you feel about this problem? How do you feel about this problem? Five, 4, 3, 2, 1. Okay.
Does it have multiple groups, or could it have one group attached?
Oh, I think Peter, there's a fair bet. If you're a betting man, I'd bet on 2 groups, 2 different groups. But if you only wanted one group, you could just not do that second step. You know, not put a second group on. Just keep cruising. You know.
Can I ask another question?
Yes, Julie. Yeah.
On the malonic ester, where does the other O leaves at the H3O plus stage?
Yeah.
The OH and the other one leaves. Is that true?
Let me see. All right, could you repeat your question?
Okay, so you said the only difference between this and the malonic ester, of course, when you start out, you're going to have the O-methyl group on the other side as well. So when you're doing all this, that's going to sit there and it's still going to be there up until you add the H3O plus on the 3rd step.
That's correct. And then the H3O plus will hydrolyze both ester groupings to carboxylic acids. So
there'll be an OH on both sides.
Yes.
And then when you heat it, one side will leave.
That's correct.
Okay, thank you.
All right. Any other questions about this? All right. So yeah, practice those. I have some in the blue book as well that you can work on as sample problems, as practice problems. All right, does anybody have any other questions about the acetoacetic ester synthesis or the malonic ester synthesis? Okay. You know, that problem is a kind of a gimme. People rarely get it wrong. I'll say that on the test. Usually people, because that's the synthesis problem too. I'm telling you straight, that's what you're going to see. You're definitely going to see that problem on the test. And so it's one that people usually don't mind too much, I don't think. Now, I don't know if people find it particularly fun, but they might. I don't know.
You don't really need the mechanism, right? You just need to know.
No, you don't need the mechanism at all, Julie. at all. You just need to know the synthetic process and understand what gets replaced and what it gets replaced with. Is that okay?
Yeah, it's good.
Okay. All right, let's talk now about the aldol reaction. Now, the aldol reaction is an important reaction because it allows for the joining of two carbon chains, and that's any reaction that allows for the joining of carbon chains is always going to be an important process. The aldol reaction itself, again, depends upon the addition of, or the removal of a hydrogen here, an acidic hydrogen next to a C double bond O. Now, this is not as acidic as the hydrogens that we were just talking about because they are connected to one C double bond O or near one C double bond O. So it's not going to be quite as good, but we can still end up getting these kinds of products because we can remove that hydrogen that's adjacent to the C double bond O. So the reagents we use here use sodium hydroxide and water, and it's fairly simple. Just heat it up and we end up getting this product right here, which is the result of taking two of these and adding them together to each other. So let's do an example of this and I'll show you the mechanism as well. Now I'll be sure here to use an asymmetric ketone that only has one set of alpha hydrogens on it, and that would be this one right here. So there's my alpha position right there. So I've got two of these, and when I add them together, the product is going to look like this. I wonder if anybody knows what these squiggly lines mean. Any thoughts? What do these squiggly lines mean? What's the meaning of these squigglies?
Cis-tran isomerism?
Yes, yeah, usually, yes, that's right, that's what it is. All right, so what it is, it's a shortcut really. It's a way to say really, so because there's no free rotation around the double bond, the possible products we get from this double bond production are going to be both of these. And rather than writing both of them down, then I can just write this with the squiggly lines there, meaning that it could go either way. Does anybody have any questions? So that's what squigglies mean. So here's another question. Will there always be squigglies? Will there always be squigglies? The answer is no. And I'll give you an example when you wouldn't show squigglies, and maybe you can see why. Maybe you can see why this one wouldn't have squigglies on it. Okay, that one would have no squigglies. Can anybody tell me why?
You have two of the same, it's symmetric on the bottom.
It's symmetric on the bottom, that's right. It's got two of the same group attached here and here. Meaning if I switched the hydrogen with that propyl group on the other side, I'm not changing anything because the groups down the bottom are the same. So you've got to be a little bit careful when you use squigglies. You only got to use them when you need to use them. Don't use them in this situation. You know I'll mark you wrong if you do. You know I will. So you have to be careful. Careful of the squigglies.
I have a question.
Yes, Julie.
Because I'm having a hard time seeing how you would get that if you had two of asymmetric, what you're beginning with.
Oh, okay. I'm actually referring to another kind of reaction that might produce these kinds of compounds.
Okay, so you wouldn't get that in this one.
Not in this one, no. There's no way. But it's possible to get it. I just haven't shown you how you might get it with this reaction, okay?
Okay.
But I think it's possible to get it. Yeah, it's possible in the crossed aldol, which is this one over here, right, which we haven't done yet.
Okay.
Okay. But I don't know that it's possible with a straight aldol reaction. I don't know. Okay. So I'm going to go through the mechanism here and show you. Well, before I actually do the mechanism, I'll show you how you can figure out what the product is going to be without even really doing the mechanism. So if you've got two of these compounds, you show the alpha hydrogens on one of them, and then you draw the other one above it with the C double bond O. And what happens is if you take the two hydrogens and the oxygen and then you join them together, that's how you can end up getting this product up here. Does anybody have any questions? I mean, it's just an easy way of getting the product without doing the mechanism. Any questions? Okay. Now that's going to come in handy later when we're doing synthesis problems, and you'll see that synthesis problems using the aldol reaction, but I'll get to that in a bit. That'll be later on. All right, let's look at the mechanism here. So as I said, the hydrogens adjacent to the carbonyl group, to the C double bond O, are somewhat acidic and can be removed by a base, even sodium hydroxide, which isn't an incredibly strong base, but it's strong enough to do the job here. After that, we can have the negative charge attack another equivalent of the same thing. And that's the important step, because that's the step where we get the two carbon chains joining together. And then the O minus can take a hydrogen off the water that's already in the solution, which regenerates OH minus, by the way, so it makes it catalytic. And this is where we end up getting what's called the aldol, because it's an aldehyde and an alcohol. So there's two of those groups there. That's why it's called the aldol reaction, because we have an aldehyde and an alcohol group, aldol. But the reaction doesn't usually stop there, because the more stable compound that can be formed is the one where we have the alpha beta unsaturated aldehyde, which has the double bond in it. At this point though, you'll notice that we can have free rotation around this single bond. So that's why we end up getting both cis and trans isomers out of this. All right. Does anybody have any, yes, OH minus. Does anybody have any questions about this so far? Yeah, there's a couple of good reasons why we end up getting a double bond here. First of all, it's conjugated. And by conjugated, I mean alternating. So that makes it more stable. Also, the double bond is quite substituted as well. And what I mean by that, it's got lots of carbon groups attached to it. We talked about that as well. So that's why we get that compound specifically rather than the compound where it's got the alcohol and the aldehyde in it. Does anybody have any questions? So this is one of the possible mechanisms you can get for question, I think it's question 2 or 3 on the test. Okay, so you can only have one mechanism question. This could be it. This one is a possibility. Does anybody have any questions about this reaction? All right, let's see how you feel about it. I'm not expecting a whole lot of this, a whole lot of people feeling good about it, but we'll see. How do you feel about it? How do you feel about it? 5, 4, 3, 2, 1. Yeah, it's probably about what I expected. Are there any questions? I mean, there's 12 people who halfway understand this, so you must have some sort of questions here. Yeah, go on, please, Anna.
Review everything first.
I'm sorry, Anna.
Oh, can you hear me?
Yeah, I can hear you now.
Oh, the reason I don't understand is because I need to review everything first.
Oh, you see, that was going to actually be the next thing I was going to say. For mechanisms as complex as this one, if I'm getting 2/3 of the class at least understanding it halfway, I'm actually kind of happy with that, because I don't expect everybody to get this right off the bat. Not until you've actually sat down, practiced it, put pen to paper, will you actually begin to really understand how these arrows are moving and what products are being formed. So that's where the whole practice thing comes into play. And by practice, I mean, I'm talking about this document here and doing these 40 problems with their mechanisms, these 40 problems here with their mechanisms, and then comparing those mechanisms to the mechanisms I have right below that, this test for mechanisms file. So as long as you're getting mechanisms that look pretty much the same as what I'm doing, then you're doing pretty well. But until you do that, you know, you're going to be dealing with the issues here. There's also a reaction types sheet here as well for those problems. See, it actually goes through and says what kind of problems those are. So if there's ones that you specifically want to practice, then you can look those up on that sheet. Okay. Does anybody have any questions? Okay. So we'll continue on here. And we'll look at the crossed aldol. Now, the difference between the aldol and the crossed aldol is that with the crossed aldol, you end up using two different kinds of aldehydes or ketones. You end up with a similar kind of product, but the catch here is that one of the compounds you're using doesn't have alpha hydrogens on it. So then there's no doubt about which one is donating the alpha hydrogens and which one is donating the C double bond O in that pattern that I showed you earlier. So let me give you an example. Let's see. You know, just for kicks, I think I might do this one. Now the pH is an aromatic ring, a phenyl group. And I'll use benzaldehyde, which doesn't have any alpha hydrogens on it. And my product then will look like this. And I'll show you how I get this.
Can I ask a question?
Yes.
You say it doesn't have any alpha hydrogens on it,
Right.
but
This-
there's a hydrogen to the right. That's not an alpha hydrogen?
No, because alpha hydrogens have to be on the adjacent carbon, Julie.
But that is,
No, adjacent means next to. There has to be a carbon here. Let me show you
it
the
doesn't
difference.
count next to the C double.
No, not directly attached, it doesn't, no. Let me explain the difference to you. You'll see in a second. That is an alpha hydrogen because that's an alpha carbon right there. Do you see the difference? There's a carbon in between, Julie.
Yes,
Hydrogens directly attached are not considered to be alpha hydrogens.
okay.
I'm glad you asked that because I'm sure that others might have had a similar question about that. So you can see that the way we do this with the pattern, it didn't matter which set of alpha hydrogens we took because it's symmetric, right? So we end up getting this as a product. I was kind of hoping it would be one that didn't need squigglies, but it does need squigglies very badly. Now the squigglies can go on the top or the bottom. I'm going to put them on the top for this one. Whoops. Squiggly, squiggly. That one needs squigglies. Does anybody have any questions?
Yeah, I
Yeah.
still would like
Yeah.
to see something that doesn't need squigglies.
Okay, you will get your wish, Julie, just not yet.
Okay,
You're going to have to be a little bit patient. I'm sorry.
that's okay, thank you.
Okay. Does anybody have any questions so far? I am going to do the mechanism for this one.
So when you said the bottom, you mean the bottom with the double bonded? O could be squiggly too.
Yeah, that's right. Well, not squiggly too, squiggly instead of. You can't have both. They can't all be squiggly. You understand that, right?
Yes.
Okay, good, Peter. Thank you. I mean, we can't overdo the squigglies. I don't want that to happen. I think that's a disaster. No, it's either top or bottom. But yes, you're correct. Okay.
What does the squiggly tell us again?
But it's actually a mixture of cis and trans, or the pH and the H can be interchanged to give a different compound. Mariam?
Okay, so now if we would draw the actual line the way that it is now, that would be trans, because the two phenyl group are on the opposite, and then on the other version would be the phenyl would be to the right, which would be cis.
Well, actually it'd be E or Z really, because it's not really cis or trans. Yeah, I'm going to take you back to organic 1 there a little bit, Mariam.
Yeah, okay.
Yeah.
It's not because it's not there's Z non-hydrogen. Okay.
Yeah. But anyway, E and Z is probably a better way of putting it.
I see. Okay, thank you.
Okay. All right, any other questions? Okay, I'm going to remove this, and I'm going to put the product up here. There we go. Okay. And we'll get in there. That's right. Okay. Okay. So let's continue on with the mechanism here. So the first step is the same as what we did before. And again, it doesn't matter which alpha hydrogen we remove, because this one is symmetric. I go into a pretty protracted discussion in this video, actually. Somebody's got a question for me, and I'll see what that question is in a second. All right, let's see what's going on. That was weird. What was weird? I've been called weird before, Jasmine, but I don't know if that's what you're talking about.
No, I had issues with technology. I'm sorry.
Oh.
Everyone was freezing and I got scared. That's all.
Oh, okay. Don't be scared. It's okay. We're all still here. If you're going to be scared about anything, be scared about the mechanisms. So the same thing happens here. The O negative takes the H off water. We end up getting this aldol compound first. And then the OH minus comes in and takes off the hydrogen, forms a double bond. And then we end up getting the product. with squigglies. Plus and H2O. Okay, any questions? Any questions about the crossed aldol here? I go into a discussion in the video that explains the importance of well, why one of them has to have no alpha hydrogens. If you had two different things that had alpha hydrogens on them, you'd end up with multiple products because you wouldn't know which one was donating the alpha hydrogens and which one was donating the C double bond O. So you could end up with a whole mess of different compounds. That's one thing. And the other thing I talk about in the video is how the reaction is set up so that the compound here that does have the alpha hydrogens doesn't react with itself and do an aldol reaction like up here. So I explain that in the video. So if you're interested in exactly how that happens, watch the video about crossed aldol, and that'll give you a good idea of what's going on. Does anybody have any questions about this? I'm not going to do a poll on this from this point forward because I know that this is one of those things you definitely have to get in and practice. You have to sit down, put pen to paper, and understand how to do these mechanisms. This is another possible mechanism that you could be asked on the test. The Novenago condensation, which is not one I'm going to do a mechanism for, this is not a possible mechanism that you'll be asked on the test, but it is possible you will be asked, or even probable, I think you'll be asked one question that relates to the Novenago condensation. And it's really very similar to the aldol condensation, except that what's happening here is that the donor of the alpha hydrogens is one of these 1,3-dicarbonyl compounds that we were looking at earlier in the acetoacetic ester and malonic ester synthesis reactions. So we know this is going to be the one supplying the alpha hydrogens because these are super acidic for the reasons that we discussed earlier. So to give you an example, we've got this interacting with, first of all, the base. Then second of all, some kind of aldehyde or ketone. We'll make it that one. And secondly, H+. You'll notice this one has alpha hydrogens too, but these alpha hydrogens are nowhere near as acidic as these guys here that are in between the two C double bond O groups. The product here, and I'll show you how we get the product. It's pretty easy. And Julie, I'm actually going to harass you this time. And I'm going to ask you if the product is going to need squigglies or not.
I'm still stuck on why that other one does have alpha hydrogens, because it looks exactly like the one that didn't have alpha hydrogens in the last. Oh, because that's a C.
That's a methyl group.
Okay.
It's a methyl group, isn't it?
Okay.
Not a hydrogen. So it makes a difference.
Okay.
All right. All right, Julie, I'm putting you on the spot here. Squigglies or not?
I would say no squigglies
Why?
because it's symmetrical, but I would say also that it's a different kind of problem. The aldols and the cross aldos didn't start with that symmetrical thing.
Right. That's true. So you can always tell, because if you're starting off with something symmetric like that in a Novenago, then you will end up with something there's no squigglies on it. But not everything starting in a Novenago is going to be symmetric. No squigglies. All right. Does anybody have any questions?
Yeah, why wouldn't it be symmetric? Because it's attaching to that area between the symmetric sides. So why would there be a situation where it's not?
If these two are different, Julie, if each side of this was different.
Okay.
Let's say I took the pH, replaced it with a hydrogen or a methyl group or something. That would
And a
make it.
Novenago could have that. Okay.
Yeah, yes, possible, yeah.
Okay.
But I wanted to, you know, I really just did this for you, just for you, Julie. I want to show one where there were no squigglies on it.
Thank you.
Because you requested it. All right, does anybody have any questions? Any other questions? Okay, now if you want to know the mechanism, it's there, but I'm not going to push that right now. The other set, the next set that I wanted to talk about are called the Claisen reactions, the Claisen and the cross-Claisen. Now, these are a little different to the aldols because we're starting here with esters rather than aldehydes or ketones. As such, something can happen here that can't happen in the aldehyde ketone reactions. I want you to focus on where I've got the cursor here, this step where the O negative comes in and kicks out the leaving group. That cannot happen when it's an aldehyde or a ketone. So we end up actually getting something a little bit different here. All right, so let's look at an example. The pattern for these is not quite as nice or as fun as the aldol pattern, but it is a pattern nonetheless. So let's have a look. Two of these will do very, oops. And I'll do ET here. There's a bit of a catch with these. The base we use has to match the ester grouping that we have in the reactant. So if I'm using OET here, whoops, then we have to use OET here and here as well. So all it has to match. So that's not very much fun, but that's how it has to be. If we don't do that, we end up getting transesterification, which means that what would happen is that this grouping could be replaced with whatever base we're using over here, if it is different. And that's not going to lead to very much fun because we'd end up getting mixtures of products. So the product here of this process is going to end up being this. I'll show you how the pattern goes just for kicks. Just so you can know how to do this without using the mechanism. So what happens is these are your alpha hydrogens. I'll just put off to the side here. That's better. And what happens is these two join together between the C double bond O and the alpha carbon of the other one, and we end up getting ETOH here as something that gets removed. And that's this bond here is the new bond. I'll do it in a different color. So that's it there. So that's how you can end up getting that as a product. Does anybody have any questions? Yeah, I know, it's not as much fun as the other one. I kind of like the other one. Okay. Let me move this over a bit. So let's do the mechanism for this one. So the base here is OET minus, which removes the alpha hydrogen, just like I did before when we were using the OMe minus. That's the same thing. And then this is the attacking step. It's very similar to the aldol up to this point. And we end up with this product, which is actually the final product, but this is not where it ends initially. Because what happens is we end up getting the OET minus formed, but because that hydrogen is quite acidic, because it's between two carbonyl groups, it actually gets lost. And then that's why we have to add the H plus in the last step to protonate it. So that can be a little bit confusing as to why we do that, but that's the reason. Okay, does anybody have any questions about this? Any questions at all?
I do. Where's that arrow going from what to what?
From which arrow are we talking about?
The first arrow, the second structure.
Okay, this one?
Right where your cursor was, a little no down. The next one.
Here.
The one over.
This one.
Yes. Where
that arrow is going onto the C.
Okay.
To form a negative charge.
Okay.
All right, any other questions?
Yeah, I have a question. I can't remember because I watched the videos and now I'm watching you go through this. Is this the only one of these that has that step where it forms it and then it has to reform it?
That's that and the cross Claisen.
These are the only two that have it.
Oh, and the Diekmann, but they're all related. You know, they're all Ester condensation reactions. I'd say all the Ester condensations do this. Okay. Julie.
Thank you.
Okay. Any other questions? Okay. So the related one here is the cross Claisen, which is the same kind of deal as before. in that they're two different esters, and now one of these is not going to have alpha hydrogens, and that's going to be, in this case, this one does not have alpha hydrogens. And again, we find that these have to match the ester groupings, just like it did in the previous one. And the product is going to look, actually, the product here is a little easier to come up with, I think. And you can see the product is going to look like this. Okay. Does anybody have any questions? So in this case, it's pretty easy to tell which one is going to have the alpha hydrogens removed, and that's the one that has the alpha hydrogens. And again, the attack is going to be on the one without the alpha hydrogens, because that's how the reaction is set up. Again, if you're interested, you can watch the video about this. And then we have that leaving group disappear. And because that's acidic again, because it's between two carbonyls, the OET minus will take that and form the anion. So the anion, you can see where that arrow is going. It's going onto that carbon. And then we add H plus in the next step, and that's how we end up with our product. Okay, does anybody have any questions here? All right, so these are all reactions that I've just talked about. You can start practicing these, and I definitely would, because it's either going to be, the mechanism you're going to get is either an aldol or a crossed aldol or a Claisen or a crossed Claisen. It's going to be one of those four. Now the aldol and the crossed aldol are similar to each other. The aldol, the Claisen and the crossed Claisen are kind of similar to each other. So really it's a choice between essentially two once you get used to doing them. But I would recommend practicing those. Practice them from the ones that are in the blue book, and I think you'll be all right as long as you can put pen to paper and actually do the mechanisms. You'll be okay. I know they look complicated, but they're not nearly as bad as they seem once you get looking at them. Does anybody have any other questions? All right. Well, we'll leave it there for today, and I'll see you all again on Thursday. If anybody wants to hang around and ask me anything, you can.
Thank you.
All right, no worries. See you later. Hannah, do you need anything?